Alright guys, welcome to section 9.4. We're going to be talking about arithmetic series today. And this whole unit's been talking about sequences, and we looked at arithmetic and geometric sequences, but now we're shifting gears into what's called a series. And a series is not really that much different than what a sequence looks like. Okay, so what we're going to do is just looking at some series today, and we're going to find them and work on some problems with arithmetic series. So what is a series? A series is an indicated sum of a sequence. So we're going to look at basically taking a sequence and adding the terms together to get a sum, and we call that an arithmetic series. It's important to realize that when we talk about arithmetic series, when we talk about terms, we still have a common difference. Okay, so when we look at series, they can also be finite and they can be infinite. A finite series, remember, has a first and has a last term. So let's look at what a sequence looks like, an arithmetic sequence, when it becomes an arithmetic series. So we have a sequence of 6, 9, 12, 15, and 18. Important to know, the common difference here is 3. What that looks like as an arithmetic series is just 6 plus 9 plus 12 plus 15 plus 18. So you could say, well, Mr. Bennett, you just took a sequence and added all the terms together. And that's precisely what I did. That's an arithmetic series. We know it's arithmetic because the common difference is an addition of 3. Okay, so what does an infinite series mean? Well, an infinite series continues without end, and it doesn't stop. Recall that a sequence, remember, like 2, 4, 6, comma, dot, dot, dot. That comma, dot, dot, dot just says, hey, that pattern continues forever. So the series would be 2 plus 4 plus 6 plus, comma, dot, dot, dot. So we're going to be looking at mostly today finite series, finite arithmetic series. So let's look at a rule that we can use to help us take the sum of a finite series. The sum of a finite arithmetic series is as follows. S sub n equals n divided by 2 times the quantity a sub 1 plus a sub n. So let's look at what each of these terms mean. Well, S sub n is the sum, okay? A sub 1 is still your first term. Now n is the number of terms. So when you look at your finite series, you got to say how many terms are from start to end. How many terms do I have there? Okay? Count up those terms, and that's your n value. A sub n is the nth term. Most of the time it's going to be your last term of your sequence, or excuse me, your series. So problem number 1. What is the sum of even integers from 2 to 100? So we're going to use our rule, okay, and substitute what we know. We're looking for the sum, S sub n. So let's look at this. A sub 1, that's 2, our first term. A sub n equals 100. It's the last term. So now you have to think, well, how many numbers are between 2 and 100 that are even? The answer is there's 50. Okay? So we're looking for S sub 50, the sum of the 50 integers, even integers. Okay, so n is 50 divided by 2 times the quantity first term plus a sub n, 2 plus 100. Simplifying, we get 25 times 102, which is 2,550. So the sum of even integers from 2 to 100 is 2,550. Summation notation. So there's other ways that we can write a sequence in summation notation. Summation notation really talks about limits. This E, it's not really an E, we call that sigma. Okay? So this is the general summation notation. You have n equals, well, wherever you're starting from, and a sub n, wherever you're ending. So your start, your finish, your lower limit, your upper limit. F of n is an explicit rule for your series. So here we just define each. A sub 1 is where you start. That's your lower limit. A sub n is where you end. Your upper limit. f of n is your explicit rule. It's important to know that a sub 1, yes, it's where you start, but it's not the first term. Okay? And I call it a sub 1 here, but I just changed it to first. So it's a sub 1, a sub n. Don't think of this as, hey, what's my first term? And it's equal to that number. And you'll see that in the next example. And one important distinction, if f of n is linear, whatever the slope of f of n is, that's the common difference. So problem number 2 deals with writing summation notation for two different series. So write each arithmetic series in summation notation. It's a series and it's arithmetic because the common difference is the same and we're adding between terms. So this is an arithmetic series. In this case, 4, 8, 12, 16. The common difference is 4. So where do we start? You might say, oh, well, we start at 4. No, let's count the number of terms. 1, 2, 3, 4. We start at the first term and end after term 4. So we go from n equals 1 to n equals 4. Writing the rule, it's pretty simple. 4 times 1, 4 times 2, 4 times 3, 4 times 4. So it's just 4 times whatever term you want. The third term is 12. 4 times 3 is 12. So there's our rule, and that's our summation notation. Okay, the second one's a little bit different. We're actually going to use the arithmetic sequence rule for explicit equations. So we have 3 plus 7 plus 11 plus ... plus 31. So I still have a start, I still have an end. So again, this is finite. However, we're missing some terms in between. So it's not 1, 2, 3, it's not 4 terms. Okay, so let's start with what we do. We write our sigma. Okay, I need a start and I need an end. So let's think. One way you could do this is the common difference is 4. So you have 3, 7, 11, 15, 19, 23, 27, 31. 8 terms. So we're starting from 1 to 8. First term to the end is 8 terms. So start at 1 and you go to 8. To get the rule, in this case I decided to use my explicit formula for an arithmetic sequence. A sub n plus n minus 1 times d. Well, a sub 1 is 3. 3 plus the quantity n minus 1 times your common difference, which is 4. I can go ahead and distribute the 4, which I get 3 plus 4n minus 4, and combine like terms. So my rule, my explicit formula, is 4n minus 1. That's the summation notation for this arithmetic series. Again, like I said, lower limit is not just putting 4 to 16. It's actually talking about the number of terms. Where are you starting with? Where are you ending with? 1 to 4. Most of the time, when you write a rule, it's going to be 1 to whatever your ending is when you're writing a rule. We'll see an example later on when we can change that. Now, in problem number 3, I've given you the summation notation, and I actually want you to use what you know to find the sum of each series. So we're going to find the sum of each of these finite series. Finite because you have a start and end. So let's look at number 1. So we have the summation of from 1 to 4, and there's our rule. Okay, so I need to know the sum of the first 4 terms. That's what this means. The sum of the first 4 terms. So we have a sub 1, 2, 3, 4. Term 1, term 2, term 3, term 4. I don't know what those terms of that series are. So I plug 1, 2, 3, and 4 back into my explicit rule. And I've done that for each one of these. Don't forget I put the negative on the outside because I just plugged in my n value. So I put the negative in red just as a caution. And when I simplify, I get negative 4. There's my first term, negative 5 second, negative 6 is my third, and negative 7 is my fourth. Add them all together. You get negative 22. That is the sum of the first 4 terms of this arithmetic series. Okay? Let's look at the second example. Now here's where we change in. I'm not going from 1 to 6. I'm starting at term 3 and I'm going to term 6. So when I do this, it's not 1, 2, 3, 4, 5, 6. It's 3, 4, 5, and 6. So really, there's only 4 terms I'm dealing with here. Even though the 6 is here, we only go from 3 to 6. 3, 4, 5, 6, 4 terms. Just like I did in the previous example, we're going to substitute 3 in for n. And I go ahead and do that in each case. Notice how the sub n matches n here. Okay, we get 11, 14, 17, and 20 for a total of 62 when we take that sum. So that's how we find the sum of a finite series when we're given the summation formula. Last little example, problem number 4. Use the values of a sub 1 and s sub n to find a sub n. Okay, so I've given you a sub 1, that's 4. Okay, and I've given you s sub 40 equals 6,080. So what that tells me is that there's 40 terms and I'm starting at the number 4. So we're really looking for a sub 40. We're looking for that last term, a sub n. So let's use our equation. S sub n equals n over 2 times the quantity a sub 1 plus a sub n. Let's substitute. S sub n is 6,080. That's equal to n is 40, over 2 plus the first term plus your last term. A sub n in this case is 40, so we're looking for a sub 40. So that's substitution. Simplifying 40 over 2 using our PEMDAS, our order of operations, I get 20, and I divide each side by 20, I get 304 is equal to 4 plus a sub 40. Subtracting 4 from both sides, I get a sub 40 is 300. So what that tells me is that the last term is 300. So we're going to start at 4. There's going to be 40 terms total. You start at 4 and you're ending at 300. And when you take that total sum of all those terms, all 40 terms, it's actually 6,080. Okay, so the next section is the last section. We're going to be talking about geometric series. If you have any questions or comments about arithmetic series and what we've done today, just go ahead and put a comment at the bottom. All right, we'll see you next time.